I would like to introduce the next speaker now, also from Bechtel. His name is Dr. Don Mazzone. Dr. Mazzone, he is Vice President of Commercial Operations in Bechtel. He joined Bechtel in 2011. Before that, Dominique was Licensing Technology Director with ExxonMobil for downstream technologies. Dominique was with ExxonMobil for more than 25 years. He also has 30 US patents, talking about the next one, for downstream refining and petrochemical technologies. Dominique has a Master of Engineering and a PhD degree in Chemical Engineering of the City University of New York. Lord, please go ahead.
Thank you, Hugo. Good morning. It is my sincere pleasure and privilege to be here this morning, and I thank Pemex for the excellent attendance and turnout. The subject of my presentation is delayed coking and environmental stewardship. People throughout the world are demanding that industrial development be done in a way that provides the products they need while minimizing the impact on the environment. The purpose of my presentation is to show you how environmental stewardship is integrated into the way we design delayed cokers. Many of the environmental challenges for a delayed coking unit are the same as for any other refinery process unit. There are, however, some unique challenges for delayed coking because of the solids handling aspect. Now, before I discuss my presentation, I want to thank especially Engineer Enrique Aguilar and Dr. Leonardo Cornejo, Enrique of IMP and Dr. Cornejo of Pemex, for choosing the Through Plus delayed coking technology for the very important Tula expansion project. It became very evident to me just how important this refinery project is, as Enrique explained to me that 40% of the gasoline demand in Mexico is imported. So we are proud, ConocoPhillips technology that we purchased, Bechtel, Through Plus technology, to have that chosen as part of the Tula refinery expansion project. Okay, from my presentation, I want to make sure you leave with three main points. One, our modern DCU technology effectively addresses the environmental issues that are unique to a delayed coker. Modern Through Plus delayed cokers have demonstrated they are good neighbors in some very environmentally sensitive locations. Bechtel Hydrocarbon Technology Solutions, or BHTS for short, can customize the environmental controls on a DCU to meet local requirements. So my presentation is organized into three main sections. First, we'll look at a typical emission sources within a delayed coker unit. Next, we'll look at how those emissions are controlled. Finally, I'll show you some examples of recent delayed cokers that have been permitted and operated in an environmentally sensitive area. Now, this slide is typical of any process unit. I apologize for the small print on this slide, but hope that you can study it more when you have the handout. What this slide shows is feedstock and energy coming from the left of the slide and products going out from the right. There are air emissions shown at the top, primarily furnace stack emissions, fugitive VOC emissions, any emissions from flaring or emergency relief. Now, on the bottom of this slide, you will see water that needs to be processed. Oily water to a wastewater treatment plant, processed water to a sour water stripper, and storm runoff water. Now, the emissions in a DCU unit are similar to those in a typical refinery unit shown in the previous slide. On the right, we show feedstock entering the process and products leaving. On the top are the air emissions from the same sources as in the previous slide, with the addition of particulate matter from the coke handling area in a delayed coking unit. The water treatment is actually less dependent on treatment facilities outside the coker because of the closed blowdown system, which is shown at the bottom left. Oily water is processed in the closed blowdown system and returned to the process. Storm water normally is used within the process. The DCU actually reduces the burden on the refinery waste stream system by processing oily water and oily solids. Now let's begin by looking at water utilization in the process. Okay, we'll start with stormwater handling because this is relatively easy. Almost always, any rainwater that falls into the coke handling area is contained within the system and leaves as moisture on the coke product. And you can see we lost some water right here, front row. In this example, typical annual average rainfall for a coker that happens to be in Malaysia, for this example, is 10 millimeters per day. Can be a lot more than that, but rainfall would need to be greater than 220 millimeters per day to result in routing excess water to the stormwater handling system. Now the bullet points, the first two bullet points on this slide addresses the streams that is produced in cooling the bed of coke. First, initially, the steam is injected into the bottom of the drum. Shortly after that, quench water is injected, and that quench water is vaporized because of the heat of the drum. As briefly discussed a few minutes ago by my colleague Rick Henneford, the steam is routed to a closed blowdown system, where it is condensed in the quench tower overhead cooler and separated from hydrocarbons in the blowdown system. Now, the sour water from these sources is routed to the sour water stripper. The main point of this slide is that all processed water from the DCU unit is contained, separated from hydrocarbons, and routed to the sour water stripper. Now on this slide, we try to show the water balance within the delayed coking unit. In round numbers, the water entering the unit is about 1/3 boiler feed water for the process heat recovery. About 1/3 is for process heat, furnace velocity steam, or main fractionator stripping steam. And 1/3 is process water primarily for quenching of the coke bed. Now the water leaves the DCU is roughly a little over a half leaves as steam and condensate, about 1/3 as sour water to the sour water stripper, and the remainder goes out mainly as moisture on the coke product. Overall, 88% of the water or steam that enters the unit is recovered for reuse within the delayed coking system that we designed. Okay, now let's discuss airborne emissions. Okay, this slide shows that everything except VOC, the furnace emissions, are the largest source of what are termed criteria pollutants that a refiner has to be concerned about. For many reasons, the design of the furnace is critical to the delayed coker. We have a whole presentation on the benefits of our furnace design that will be presented by Alberto Pina later today. The numbers on this slide show a furnace with low NOx burners and without selective catalytic reduction. What I want to focus on are VOC and PM emissions. For VOC emissions, we need to pay a lot of attention to fugitive emissions from the process. The PM10 micron emissions from coke handling are quite small in quantity. However, we recognize larger coke particles can create a mess if not properly controlled. Many of the dust control methods we'll discuss only control the regulated PM10 particulate matter, but also control coke dust. Okay, we'll start our look at airborne emissions with volatile organic compounds, or VOCs for short. Before we start looking at control systems, this slide gives an approximation of the VOC emissions from a coker compared to the rest of an integrated refinery that we have analyzed. In this case, tankage contributes over 50% of the VOC load from the refinery. Hydroprocessing was next at about 15%. Delayed coking and gas processing were about equal at 10% each. Everything else added to 15%. So as you can see, although 10% of the VOC emissions is significant, the DCU is clearly not the largest producer of VOCs. With that said, let's take a look at VOCs in the delayed coking unit. So one area of process VOC control that has received much attention lately is opening of the coke drum to the atmosphere after the drum has been filled with coke and cooled with quenched water. Typical for new cokers, the pressure must be reduced to about 0.35 bar. Some locations have required 0.15 bar pressure reduction. This schematic shows how that low pressure is accomplished. For the quench cycle, water enters the bottom of the drum and is vaporized. Steam leaves the top of the drum and is condensed in the quench tower overhead cooler. During this period, the non-condensable vapors are routed to the main fractionator. At the end of the quench cycle, an ejector is used to reduce the pressure on the settling drum to almost atmospheric pressure. Okay, turning to particulate matter, the emission sources that are of most interest are the solids handling system in a delayed coker. We will consider two areas of the delayed coking unit, the pit pad area and the coke handling and storage systems areas. Okay, let's look at the pit pad area. On this slide, we'll look at the control technology that we use for reducing PM10 and dust emissions. We start with where the coke falls from the drums. It starts by sliding down a slope wall that acts as a barrier between the coke handling area and the process unit, and Rick described previously. The whole coke storage area is surrounded by high walls. These walls, along with the slope wall, effectively keep coke out of the process area of the DCU. Now, after falling down the slope wall, the coke then enters a pit filled with water that keeps the coke fully wetted. Now, from the pit pad, the coke is moved with an overhead crane to the pad, where it decants to about 8% moisture. With an overhead crane, there is no dust generation as there would be with wheeled vehicles. Now, after about 24 hours on the pad, the coke is loaded into a coke crusher that is located inside the high concrete wall, so any spillage goes back onto the pad. Now, finally, there are water sprays located around the perimeter to maintain moisture on the coke as needed. The mode of transportation that will be used to move coke from the refinery has a large impact on the design of the coke handling and storage system. Most of the features shown here are typical of all coke handling systems. Those are things like maintaining proper coke moisture, an enclosed conveyor system, enclosed loadout system, dust control at transfer, and loadout points. Now, the type of coke storage, open or closed, and the amount of storage is also dependent upon the mode of transportation. Now, trucks generally require less coke storage and ships require the most. The point is that dust control can be effectively accomplished, but these are engineered systems and it takes an experienced design team to make that happen. The point of this slide is that there is various options for coke storage, and these options vary in the amount of fugitive emissions that exist and also the dollars involved in implementing these systems. And each refinery is unique in what type of system they can accommodate. Now, I'm going to gloss over this slide because Rick did a good job in outlining blowouts and concerns of blowouts in a delayed coker unit. What I do want to briefly mention is the things that minimize the occurrence of blowouts. Maintaining the proper coke drum reaction temperature usually means keeping the coke drum overhead temperature high enough to complete the reactions. A proper flow of feedstock into the drum is critical. Bottom and heading valves are a great invention, but they require different feedstock entry piping. In many cases, a single side entry into the drum results in flow up one side of the drum, and the material on the other side of the drum cools and does not react fully. The local quantity of unreacted feedstock inhibits proper quenching and leaves hot spots inside the coke bed. Then we're back to the problems in the previous slide. Dual inlets have virtually eliminated this situation, and Rick has a presentation on dual inlet to follow shortly. Now, watching the VM content of your coke is a way of verifying that the coke bed is operated at an adequately high reaction temperature. Finally, quenching procedures are important to ensure that the coke bed is fully quenched prior to cutting the coke from the drum. Now I'd like to discuss some case studies that I'd like to share with you. The first one is Tesoro Golden Eagle Refinery in Martinez, California. The Tesoro Golden Eagle coker replaced an aging fluid coker. As you can see from the bar chart, there was a small increase in VOCs, but a huge reduction in the remaining criteria pollutants. Of more interest is the location of the new delayed coker. The Golden Eagle Refinery is located in the San Francisco area of California in the U.S., and that is renowned for their environmental activism and stringent environmental controls. The Golden Eagle coker has been in place since 2008. The WRB Wood River Refinery is located in the central part of the USA. Interesting point I would like to make with this is that it's in the vicinity of a housing area. The area in the upper left corner of this picture is a residential neighborhood. It is separated from the refinery by only a road. The WRB Wood River DCU began operation in 2011. Finally, there is a picture of the Hovenza St. Croix Refinery in the U.S. Virgin Islands. The refinery is adjacent to a wildlife refuge. The Hovenza DCU started operation in 2002. So in summary, I want to leave you with three main points, as I mentioned previously. Our modern DCU technology effectively addresses the environmental issues that are unique to a delayed coker. Modern through-plus delayed cokers have demonstrated they are good neighbors in some very environmentally sensitive locations. BHTS can customize the environmental controls on a DCU to meet local requirements. And with that, I thank you very much for your attention. Be happy to try to answer any questions you may have.
Thank you, Don. Any questions, preguntas, por favor?
So if you have questions later on that you would like to ask myself and our team, we have a table and a booth right next door. And you can also ask us during lunch, which we're sponsoring. Thank you.
Thank you all.